Okay, let's suppose Audacity runs an experiment where they test changing the color and placement of the Start Now button. Their metric is click-through rate, and they divert by cookie. Their practical significance boundary is 0.01, and they use an alpha of 0.05 and a beta of 0.2. Now here are the results of the experiment, which was run over 7 days, and the total numbers are on the last row. I won't go over it now, but if you do a sanity check, you'll find that the number of page views is comparable between the two groups. So let's start analyzing. Now in lesson 1 we analyzed a similar experiment, but we measured click-through probability instead of click-through rate, so we could assume a binomial distribution. With click-through rate, like I mentioned in lesson 4, the distribution is more likely to be Poisson, which is harder to deal with analytically than the binomial. So this time, in order to calculate a confidence interval, it's a good idea to estimate the variance empirically. In fact, Audacity already calculated the empirical standard error when they decided what size to use for their experiment. With a sample size of 10,000 page views in each group, they had measured the standard error to be 0.0035. As in lesson 4, I can assume that the standard error is proportional to 1 over the square root of n. However, n here was the sample size of one group, which works well if there's the same size in both groups, as in the estimation of the standard error, but in our results, there's not the same number of page views in both groups. In this case, I can assume that the standard error is proportional to the square root of 1 over n1 plus 1 over n2, and this should work well if the n's are fairly close. This should also look familiar. It comes up in the formula for pooled standard error in the binomial distribution. So then the standard error for our experiment can be determined using this equation, where the empirical standard error divided by the empirical scaling factor is equal to the standard error for our experiment divided by the scaling factor for our experiment, which involves the number of page views in both the control and the experiment group for our experiment. So then the standard error for our experiment comes out to 0.0041. Now I'll replace this table of results with just the total numbers to make a little more room. Now I'll estimate the difference between the click-through rates in the control and experiment groups by subtracting the control estimated click-through rate from the experiment estimated click-through rate. And this comes out to 0.0300. Then the margin of error is the standard error times 1.96, which comes to 0.0080. Then the confidence interval is from 0.0020 to 0.0380. Based on this, I would recommend launching the experiment. The confidence interval does not include the practical significance boundary of 0.01, meaning I can be confident at a 95% confidence level that the true change is large enough to be worth launching. However, just to double check, let's look at the results of the sign test. To do this, I'll need to bring up the day-by-day data again. Here, to the clicks columns, I've also added the click-through rate, so that's just the clicks divided by the page views for each row. To do a sign test, I need to know the number of days, which in this case is 7, and I also need to know the number of days with a positive change. So comparing the click-through rate in each row, I can see that the experiment group actually had a higher click-through rate on all 7 days. This certainly looks good for the experiment, but what would be the chance of this happening randomly? If there was no difference, then there would be a 50% chance of a positive change on each day. So the question is, if you flip a fair coin 7 times, what is the chance it comes up heads 7 times? This is the same calculation I did earlier to do a population count sanity check. Earlier, I used a binomial distribution where each event was a cookie, and the 2 outcomes were being assigned to the control group or the experiment group. Here, the event is a day, and the 2 outcomes are a positive change or a negative change, and the probability of each outcome is 50%. The main difference is that here we cannot assume a normal distribution, since 7 days is not enough for the binomial to closely approximate a normal. You can do the calculation by hand using the probability density of the binomial distribution, but there's also an online calculator that you can use, which is linked in the instructor's notes. I'll use the online calculator. First, I'll need to enter the number of successes I observed. I'll define a positive difference, or the experiment group having a higher click-through rate than the control, as a success, so there were 7 successes out of 7 total days. Then I'll leave the probability at 0.5 and click Calculate Probabilities. The number I'm interested in here is the two-tail p-value, which is 0.0156. That's the probability of observing a result at least this extreme by chance. Since this is less than the chosen alpha of 0.05, the sign test agrees with the hypothesis test, that this result was unlikely to have come about by chance. Given this, my recommendation would not change. I would definitely launch the experiment with increased confidence in the experiment results. Now I want you to do the same analysis for this table of results. Again, The metric for the experiment was click-through rate, and the practical significance boundary is 0.01, and the alpha is 0.05. These are the results for the first week of the experiment, and these are the results for the second week. I've put the click-through rate instead of the number of clicks in these columns to make the analysis a little easier. You can also find these results in the spreadsheet linked in the instructor's notes. Audacity also empirically estimated the standard error for the click-through rate to be 0.0062 with a sample size of 5,000 page views in each group. Like I did, you should both do a sign test on the day-by-day data and compute a confidence interval of the effect size. That is, the difference between the click-through rate in the control group and the experiment group. Put the lower and upper bounds of your confidence interval in these boxes, and the two-tailed p-value for your sign test in this box, all to 4 decimal places. For each test, are the results statistically significant at the alpha equals 0.05 level? Finally, discuss on the forums what recommendation you would give if you saw these results in an experiment you were running. Would you recommend to launch, not launch, dig deeper into something strange looking? Would it be a judgment call that depended on the business strategy? Once you've discussed your thoughts, check this box.